My name is Michael Schuldenfrei. I'm the Chief Technology Officer for OptimalTest, and I'm going to talk a little bit about the industry trends that have been driving some changes in our applications over the last few years, and we'll be showing you how that impacts the functionality in our tools as well. When we started work on this about 8 years ago, it was very clear to us, and from everything we've been hearing from customers and from the experience that we had in the industry, that the main focus for our tools needed to be yield, efficiency, utilization. Those were the areas where people were really looking for their test processes to improve. But in the background, things were beginning to heat up, and electronics are being used in more and more places where quality was the overriding concern. And it started, of course, with everything to do with aerospace, aeronautics systems, and so on. And now, more recently, it's become very prevalent in the automotive market. Today, you have drive-by-wire. The steering wheel isn't even connected to the wheels anymore. It's all being done by computer chips. And of course, the cost of an RMA, or even worse, of a recall for a car manufacturer is extreme. And therefore, the whole issue of quality and ensuring that no bad chips make it into a car, even to an audio system in a car, has become absolutely critical. And in fact, it's even gone as far as the consumer electronics. No one wants to have a smartphone that fails. No one wants to have a tablet that fails. Anything like that is considered very bad news for the suppliers of this equipment. So we've understood, and we've been driven by our customers to a very large extent to understand that what we really need to solve is the quality issue. So although our systems are still very much focused on yield and utilization and so on, we felt the need to increase our ability to provide better quality for the products. And the way we're doing that is, if in order to increase yield or to increase efficiency and increase utilization, what you're actually trying to do is you're trying to look for parts which were wrongly labeled as bad parts and turn them into good parts by recovering them through retests, for example. What you're trying to do when you're talking about quality is you're trying to look for parts which were wrongly labeled as good parts and turn them into bad parts, prevent them from shipping, and ensure they don't reach an end customer. When we're looking at RMAs, return merchandise authorization, that's, I'm sure everyone's familiar with the term. That's when a chip gets returned to a supplier. There are different names for that for different customers. But when we look at the causes, the root causes for typical returns, and this is data we got from one of our customers, but we've seen similar numbers based on analysis at other customers as well. What we're actually finding is that somewhere in the realm of between 40 and in some cases up to 60% of customer returns can be traced back to the testing process. So if you actually take a look at the chip was manufactured perfectly well, but the problem was at test. Either it was a bad part and it's failed at test, or it was tested too many times, and so on. All sorts of different causes that are actually rooted in the testing process itself. And what we're trying to do nowadays is we're trying to eliminate these parts which manage to escape the testing process, and therefore we've created a new solution which is called escape prevention. And I'll be talking about that a lot in the next slides. So what is the challenge in performing escape prevention? There are actually several challenges. The first challenge is everything that comes under the umbrella of what's becoming more and more widely known in the database world today as big data. Okay, the complexity of your parts is increasing over time. Typical chip now may have as many as 2, 3, 4, 5,000 parametric tests, possibly even more than that, being collected at each operation. The speed at which you're collecting that data is growing over time because the testers are more powerful, the workstations are more powerful, and so on. So overall, the volume of data is increasing significantly. Plus, we're trying to bring in data from more and more sources. So if, for example, 2 years ago, OptimalTest would focus only on wafer sort and final test data, we've now progressed to supporting e-test data or watt data, as we already presented last year. We also handle SLT data, burn-in data, data from other operations. And of course, we now want to begin to tie that stuff back into design data as well. So anything that might be coming out of tools like Synopsys and so on, these are all tools that have interesting data from the perspective of analyzing test escapes. And one of the things the system that's going to handle this kind of data needs to do is it needs to handle big data. One other area that causes the data to increase significantly is the amount of time that typically passes from the moment a chip is tested or starts being tested, for example, at wafer acceptance test in the fab, until eventually that part is returned by a customer as a faulty part. That can easily be 18 months or 2 years. How do you find historical data from 2 years ago in a database which will typically be having its data purged, let's say, every 6 months or 7 or 9 or 10 months or whatever? The second challenge is the expertise. So you've got all of this data. You've got a part which has gone through, I don't know, 10, 15 different test operations. At each operation, it's generated thousands of parametric test results again. And all in all, you've got your one failing part in a wafer, or possibly a collection of failing parts from different wafers, each of them with different attributes. How do you mine those huge volumes of data in order to find the information that's really relevant to you? And how do you know what kind of issues are occurring typically in chips, possibly generally in the industry, to know where you need to focus your attention? Another area is time. Craig talked about this a lot. It's one of the big advantages of working with OptimalTest. Data logs arriving after 2, 3, 4 days are typically too late for you to be able to handle any kind of escape prevention. For example, if we determine that there's something wrong on a tester and you know about it a day after it happened, if that wafer has already gone on to the next stage or even worse, gone on to assembly, it's too late. You can't do anything to stop that part from being shipped. And finally, of course, there's everything to do with cost. Everyone knows that the cost of RMAs now is escalating. It's become a real focus issue for CEOs of large organizations. Everyone is looking for a way to reduce the overall cost of this issue and try and find the solution for all of these return parts. So going back to OptimalTest's overall set of solutions that we provide to our customers, up till today, we've really been focused very much on yield recovery, on efficiency and optimization, as I talked about. We also have everything to do with throughput, which is test time reduction, adaptive test, and so on. All of these capabilities have been around now for some time in our solutions. They're deployed in production with various customers, and they're doing a good job. And now the whole emphasis has moved here to the quality and reliability block. Now, it's not that we've stopped doing any of this. Quite the opposite. We're continuing to enhance those capabilities. And again, as Craig explained, we've been able to achieve some pretty significant results at NVIDIA and our other customers. But still, the focus now is quality and reliability. So what does OptimalTest bring to the table when we're talking about quality and reliability or overall? First of all, there really are 3 pillars. The first pillar is the pillar of data. We have the tools and the capability and the infrastructure to be able to bring the data in from the subcons or from your test houses. So for example, if you're an IDM, you've got your own internal test floors. We use exactly the same methodology. Or in some cases, we even have IDMs who use a mix of internal and external suppliers. All of those are supported. We can bring in all of that data cleanly. We can bring it in fast. And we can ensure that you have a coherent and complete data set from which you can perform analysis. On top of that, we've got all of the tools. So up to now, I've been talking about getting data into the design center of your organization. We also have all the capabilities to create rules based on the analysis that we perform, and then publish those rules back out to the supply chain. And again, it'll work whether it's an internal test house run by your organization or an external OSAT if you're a fabless company, and so on. So all of the automation capabilities in those tools, the ability to trigger alarms and alerts so that engineers know when something is going wrong. You don't have to dig through tons and tons of data in order to find the problems. The problems come to you so that you can solve them. And additionally, there's a whole load of automation around preventing things from happening in the first place. So for example, if the system detects an escape, we don't just send an email and hope that the engineer happens to be available or isn't on vacation this week. We can actually interact with systems at the various subcons, run processes to ensure that those particular parts don't get shipped. We can bin them out, for example, using inkless bin maps. And we're integrated at all of the subcons or almost all of the subcons that are active today in the supply chain. And finally, OptimalTest brings a lot of expertise to the table. We've got engineers who've been doing this now for slightly more than 8 years already. We've been working with the 5 largest fabless companies, with some of the largest IDMs, with subcons and so on. We have teams of technical teams deployed throughout Asia who are actually available and can go to the various subcons in order to help the subcons resolve issues that the system has recovered. All of that expertise, together with the tools, together with the capability and the data flow, make the whole system an extremely powerful system. So where are we today? We're growing each year. We've added a couple more large fabless customers in the last year. And when I say we're deployed at these places, we're talking about almost complete deployment. For example, at NVIDIA, we're already in all of their wafer sort and e-test operations. We're currently finishing up the final test operations, shortly adding in all of their functional test operations as well. At most of these other customers, we've already deployed on at least 3 or 4 of those sockets as well. We're testing something in the region of 25 million chips a day. That comes out to something like 10 billion chips a year. And from 10 billion chips a year, you can learn a lot about the issues that are common across the industry. And we can take that knowledge and we can pass that knowledge on effectively to new customers so that they can benefit from that knowledge. In addition to installing for our customers have driven us into their supply chain. So we now have servers installed at all of the companies you can see here and more. Those servers are connected to all of the testers. We have software running on hundreds of testers at these locations, which means if you're a new customer of OptimalTest and you want to join the bandwagon, or if one of our existing customers wants to start using a new subcon that they haven't yet used before, it's very easy for us to enable those additional testers and provide that service for them. This is a slide we've shown before, although we've made a few minor changes in the last year or two. But for those who are unfamiliar with it or perhaps have forgotten, I'll just go quickly over the architecture of the OptimalTest solution. This is a very high-level architecture. Of course, beneath the hood, there's a lot more detail. So here on the test floors themselves, and again, in the internal or external supply chain, we install a software component called OT Proxy. OT Proxy is a very small software component. It has 2 primary tasks. Its first task is to monitor the tester and collect data log information. Its second task is to interact with the test program in adaptive test scenarios. So for example, if we're doing test time reduction, it'll be the OT Proxy which will be toggling tests on and off based on the test time reduction rule that has been provided. We can also interact with the tester in other ways. For example, in critical situations for customers who've bought our online solutions, our real-time solutions, we can actually make a tester pause. So if we detect some kind of significant excursion, we can stop the tester and prevent that excursion from continuing. So all of the data collected by these testers, by OT Proxy components, are sent to the proxy server component, which is a server or set of servers installed at the test house itself. Those servers collect all of the data. They can also augment that data with additional information from MES systems. So for example, very often data logs don't contain product identifiers or other pieces of information that's useful. We can pull that information from the MES system. We can also pull information from MES such as quantity in, quantity out, and so on. So we've got a way of validating that the data we're seeing in the tests, in the data logs from the testers, matches the actual throughput or matches the actual lots and wafers and products and so on that were actually tested. Additionally, and this is what I was talking about before when we were talking about escape prevention, we have connectivity between our system and the wafer map repositories of the various subcons. So we can perform bin switching operations in order to kill bad parts, a part which may have received a bin 1 in test, but we've determined needs to be changed to a bad bin. That's something that we can do through the integration with the wafer map processes. And that's how we can prevent bad parts from being shipped. Now, once we've collected all the data, we send that data to a server located at the fabless. Of course, there's a lot hidden behind the scenes, handling security and so on. One thing we don't want to see is data from customer A going to customer B. So obviously, there's a lot of intelligence there, making sure that that never happens. Once the data arrives, and it'll typically arrive within 5 to 10 minutes from the end of test. When I say arrive, it means it will have arrived, been loaded into the database. It would have been processed using our rule engine. And if necessary, an engineer who needs to receive an alarm will have already received that alarm. So within 10 minutes of the end of test, you can actually take an action, perform an action to prevent some kind of problem or to deal with some kind of problem. And we connect, of course, to the email servers and so on in order to provide that capability within the subcons. So if we're talking about quality and things that we can do with quality, There are some low-hanging fruit, and we'll get to those in a few minutes, but some of the most interesting stuff that we're talking about today, and again, Craig discussed this a lot. In fact, Craig and his team are really pioneering a lot of this at NVIDIA. Everything to do with data feed forward, real-time data feed forward is something that NVIDIA are leaders in today. What we're doing today is we are able to collect the data from all of these different test operations, just as Craig explained. And based on that, we can then make intelligent decisions. By analyzing that data, we can make intelligent decisions across different operations based on the data that we're seeing. So you can take information such as parametric tests, such as the location of the die on the wafer map and so on, to build what we're calling a quality index. And that's something we'll talk about a lot next year, in next year's presentation, so come back. And we can use that data in order to really ensure that the parts that should get shipped are getting shipped, and parts that shouldn't get shipped are getting killed and not reaching the customers. Let's take a look at some examples of the kinds of escapes that we've discovered at customers, and I need to tell you that it's quite remarkable. One of the things that we do in our sales process is we do data analysis for many customers. Data analysis consists of taking data logs from several products for many hundreds of thousands of parts, typically, and we look at that data and we try to find patterns or problems or issues. And the thing that's really remarkable is that we found that many of the problems that we discover at one customer actually repeat across different customers. We don't always understand the cause, but we do understand the signature of the problem, and it is something that needs to be dealt with. So in this example, we've got a particular parametric test, which was being tested on 2 sites. You can see red and blue colors here for the different sites. You can see that both of these sites were testing more or less regularly at around the level of 350 here, until suddenly one of the sites started to go out of spec. Now, that could be a typical site-to-site issue, right? It's not something that would necessarily be a major problem. Eventually, some of the tests started failing, but, and this is the remarkable thing, in this particular example, all of these units received a good bin. Now, as I said, we don't know why that happened. There are all sorts of issues that can happen with the test program. There are issues that can happen with the tester. We have hypotheses. In fact, some of our customers have found the root cause based on different things that they've discovered on the tester afterwards. But the signature is still there. It's very clear. You have a test here which should not fail. The results should not be above the upper spec limit, yet they are. And yet still, for some reason, that unit received a good bin. These are the kinds of things that we've been seeing, and we do see very frequently in customer data. Another example that we have is what we call freeze. You can see here that we have a lot that was under test. Each of these lines and dots here is a set of units that were being tested in parallel. And all of a sudden, we can see here at the end that the test results, instead of having this sort of general spread, all of a sudden the test results were spread over a much smaller range of values. Now, that is extremely suspicious. It's probably something to do with the hardware or the probe card or something like that. It certainly means that the tests for all of these parts is not reliable. One of the things that we can do is we can discover these kinds of issues on the tester as they're happening or immediately afterwards using our offline rules and alert the user and possibly even perform a bin switching task to prevent those parts from reaching a customer. Another example here, I think everyone does know what the cause is. This is a classic one. It's everything to do with over-probing. Okay, there are typical industry standards about the number of times you can place a wafer on a chuck and the number of times you can test the wafer once it's on the chuck. And yet we see over and over again, when you look at aggregated data across all of the operations performed on a particular wafer, you see situations over and over again where the same die was probed multiple times. And of course, when you're probing the die multiple times, you're damaging the pads, the contacts, and making that part a suspect part. It's a part you probably don't want to ship. For example, I wouldn't like a part which has been tested 16 times to be placed in the ABS controller of my car. So what we're going to do now is we're going to switch over to a live demonstration and show you how the tools can actually help us find some of these issues.